Hi, so here's another little simple simulation, and this is one where I have a target and then something that's aiming for the target. So here I have something set up where you can see the path, and you can see that initially down here on the bottom there's a target, and then there's something that's trying to home in on that target, and in the beginning it's not at the right angle oriented towards the target, and then you can see initially it kind of moves over and kind of aims itself for the target, and as it gets closer it comes in contact with it, and so you can see here it closes in on the target, reorients itself at the beginning. I have it set up so that when the two come in contact, when the closing velocity actually turns negative, then the two objects are just deleted from the simulation. And I have it set up in geometry nodes. If you've seen some of the other videos that I have, I had a setup where I had a fourth order Runcutta time simulation, and this is a second order, and this is the total geometry nodes setup. Looks like a bit of spaghetti, but it's not that complicated. The geometry is just 2 points that are joined, and then each of those points I do an instance on points for a cylinder, and those are the two objects that I have, kind of a target and then another object that's kind of homing in on it. RT and RM are the positions relative to the origin of the global system. And if I turn on the annotation, I can kind of write out some of the equations. This is stuff you can find on Wikipedia if you look it up. It's a proportional control law. And so this is the target, and the other, let's call it a missile. If you look up, there's a guy named Zarchan. He has a book, and this is like one of the first problems. It's like a World War II era kind of proportional control law. So this is the target velocity, and then this is the target acceleration, and then down here, assume these dotted lines are parallel to the y-axis, and here I'm some of the notation is 1, 2, and these are the y and z axis. So there's a lambda angle. That's the angle between the target and the missile, and then there's an angle between the vector for the velocity and the vector between the two positions, and that's a lead angle and a heading error. And there's the velocity of the, let's call it the missile, and there's a proportional gain, that's that NP, and we'll figure out what that is later. And one of the crucial things to calculate is the RTM, which is just the difference between the position vectors. And then there's an angle beta, that's kind of orientation of the target relative to the y-axis. And so that lambda angle is just this RTM. You separate it, and then take the arctangent of those two, and that gives you the lambda angle in radians. So if we go back out, you can see some of the inputs are beta, the magnitude of the target and the magnitude of the missile, VT and VM magnitude are those two. And that's just a conversion between beta, given in degrees, which is 90 degrees, and beta, which is given in radians, which is just, pi over 180 degrees. So that's the L. If you look at some of the equations I write, that lead angle is that L. And then the VT is just minus VT, which is the magnitude. That's the y component of the target velocity times cosine beta. And then the z component is just VT sine beta. And so if you go into this block, you can see that there's calculations. A lot of things I'm just routing through, and I did that just because to me it kind of made things a little easier to keep straight. Otherwise, it turns into just a mess of node lines, the little noodles going between the various nodes, and it gets a little confusing. But if I pass them through, it kind of cleans things up. So first thing you do in here is there's a equation for the lead angle, which is the arc sine of this quantity, which is VT, and the sine of beta plus lambda. You can see I'm calculating that here. Then I need to divide that by Vm, and then take the arc sine of that whole thing. And so that's really the main thing in this block, other than the VT calc, which is pretty simple. You just have the beta and the VT magnitude read in. And if I dive into this, you can just see there's a sine and cosine. And then those both are multiplied by VT. And then the y component is multiplied by -1 to get the negative sign in there. And then there's a combine XYZ to get the y and z components in there. And then the output VT. And I'm feeding through just the beta angle in radians. So I'm showing you a little detail here. These nodes are actually repeated inside the simulation zone. So if we go through them once here, then we don't need to go through them again. They're just repeats, just copies of what I'm showing you right now. So there are some other things to calculate. And if we continue on out of here, we want to get the Vm. And these are just to get the initial components of Vm. And what those are is Vm naught is Vm cosine, the lead angle, plus the heading error, plus lambda. And then Vmz is just the sine of that same angle times Vm. And so if we dive into this, you can see that that's exactly what's being calculated. Heading angle is given in degrees, so I do the radians conversion. Theta is what I'm calling the lead angle plus the lambda. And then those go into the cosine and the sine once they're added with the heading error. And then they're multiplied by the magnitude of Vm. And so VTM is similar to the RTM, which is just VT minus VM, those two vectors subtracted from each other. And so if you want to calculate the rate of change of lambda, we can dive into this node, and you can see I'm pulling out the components, the y and z components of VTM and RTM to calculate that. And the equation for that is lambda dot is RTMY VTM2 VTMZ minus RTMZ VTMY over the magnitude of RTM squared, and the magnitude is just the square root sum of the squares, and that's shown there. So that's really the only thing being calculated here. Everything else is just being fed through to make the nodes a little more comprehensible, at least to me. So once we dive out of that, some of these inputs are used to calculate, let's see, which one are we going to go into next? Probably the VC calculators. That's the closing velocity. And the lambda dot is what's used in the proportional control law. You can look it up on Wikipedia. And prime, which is XNP, that's just a gain. VC is the closing velocity, the closing velocity between the target and the thing that's homing in on it, and then that lambda dot. And so VC is another quick calculation, and if I write it out, it's minus RTM dot, which is minus RTMY VTMY plus VTMZ RTMZ, and that quantity is over the magnitude of RTM, and that gets you VC, and that's what's calculated here. Since RTM is a vector length, that's the node that you need to actually calculate that magnitude, and that output is VC. And so once I have VC and lambda dot, you can see those two are multiplied, and then those two are multiplied to get x and c, which is actually the acceleration. And so I have a x and t, which is the target acceleration, and that goes into calculate beta dot, and that is simply dividing that x and t by the vt magnitude. And then after that, we're going to dive into the calculations for the acceleration of AM. And you can see that's just sine and cosine of the x lambda, and those are both multiplied by x and c. The y component has a negative sign on it, and then those are combined. And here I'm writing out those equations. XNP sine lambda and XNP cosine lambda. You can see that AMY is a negative sign. And so those are fed into the simulation zone, and then the Runcutter method has two steps. First, you calculate VT. You save the VM old, RT old, and RM old. And this is a second order Runcutter, so it's not as complicated as ones that I've shown in other videos. And so beta dot is calculated just like we did before, XNT over VT. And then if we go into this first step of the Runcutter, we're just doing the same calculations. VTM and RTM go into the VC calc. XLAM is calculated, XLAMD is calculated, and then AM is calculated, just like we did outside the simulation zone. And then once we have these, we're calculating like the first increment of RT out, which is RT times H, which is the time increment, times VT, beta plus H times beta dot, VM plus H times AM, and then RT plus H times RM plus H times VM. So those are all the calculations there. And then these are the step one. In between, we're calculating VT again. And then here's the second step, and it's exactly the same as the first step. If we dive in here, you can see it's the same node setup. And the same things are calculated. But the inputs are not the old values. They're sort of the intermediate values that are calculated in the first step. And those go into the new calculations of RT, RM, and VM. And then finally, those are combined, and it's the VM old plus the VM new, the old plus what comes out of that second step, and the same for RM and RT, and those are the final values once you divide them by 0.5, and that's just the math of the run cut a second method, second order method. And then beta, we're calculating that again. This is the beta final, and then that's added to the beta old, and then that goes into the final beta that's fed through the loop. And up here at the top, I was saving some of the attributes just as I was sort of working out the math and making sure it works. The positions, I have an index so that I can set the position of either the first object or the second object. The first one has an index of 0, the second has an index of 1. So if it's equal to 0, I'm setting the position of the first object, and you can see here that's RM, and then a little later in the setup you can see I'm setting the position of the second object, so that's RT going into there. And I have some rotations in there too, so I'm taking subtracting the old RT from the new RT, and the same for the RM. I subtract those two, normalize it, take the dot product because I want to get the angle between those two vectors, and this is the dot product with just the z-axis vector. I take the arc cosine of that, and I'm using that as an x rotation. And here I subtract the rotation from the angle that I'm calculating, and I had to kind of fiddle with that a little bit. You can see there's the rotate Euler that goes into those rotation blocks. I'm sort of fudging the RM one. I kind of needed to add an angle in there to get that to work. And then in order to make them disappear once they get together, here I have VC, and what I say here, if the index is less than 2, which is both those objects. I initially had planned to do something a little more elaborate, but I just have those 2 points here. And then VC, if that's below 0, and there's a Boolean and, so if both those things are true, then it'll go ahead and delete those 2 objects. So when they come together, the VC turns negative after it closes in on the object, And then on the outside, you can see I'm just setting a material and feeding that to the output. And then here I'm showing what happens if I don't realize those objects. Then no path is traced. I have on the cube, which is the geometry nodes setup, I need to have that realized instances, or else what I'm doing here is a dynamic paint displacement. I also did some with waves to kind of see how that looked. And if you don't realize the instances, then it doesn't have the geometry to go ahead and do that dynamic paint. So the brushes are the two geometry nodes objects, and then those are it's just a plane for the canvas. And so that's really it. I did a simulation also with some ships instead of these cylinders. So it could be used for, say, you have a pirate ship that's closing in on another ship, and you wanted to see how those close in on each other. You could do it that way. And you can change the inputs and the heading angle and everything, and the simulation kind of runs on its own. You don't need to do anything to, except for maybe the rotation of the object. You might need to fiddle with that a little bit. But it's a simulation. You don't need to set any keyframes. I guess you could. It might be easier just doing it that way, setting some keyframes. But the point of this is to do something a little more complicated than just setting keyframes. Do something a little more mathematical. So if you like this kind of thing, go ahead, hit like, subscribe. I appreciate all those who have up to now. And so Happy New Year. It's 2024, and I hope to see you in the next one. All right. Thanks. Bye.